Hello, welcome all at the second talk of PySport. First, I'm gonna introduce myself a bit, like my affinity with PySport. I'm a professional hockey player and a data scientist, so maybe nice to know. Now I'm gonna give the word to Max and Matthias. We're gonna talk about computer vision at the Dutch Tennis Federation. So give them a warm round of applause, please.
Thank you so much for the introduction. So we are M.Brouwer, data scientist from the Dutch Tennis Federation, culminating, and myself, Matthias. I'm an assistant professor of data science in sports at the University in Groningen, and this is a cooperation project where we try to help the Dutch professional players to finally win a Grand Slam. we are ambitious, I mean. And therefore, we try to use computer vision to up their game a little bit. Normally, when you think about computer vision, most of you guys, when it comes to tennis, will think about Hawkeye and the typical application of Hawkeye, which is mostly the electronic automated line calling, which, yeah, you can be curious how accurate this actually is. But it gives at least nice visualizations and results. But next to that, they also provide ball and player tracking. So they also provide X and Y coordinates that you could actually use for way more ideas like tactical analysis, load monitoring, and so far. The problem with that is that such a Hawkeye tracking system uses like 8 to 13 cameras per court. So actually installing it, setting it up takes quite some time. And it also costs around 100,000 euros per court. So, and if you are a little bit busy in sports, you know sports federations don't have money. So if they would do this at their center in Amstelveen, where they have at least like 5 indoor courts, that will already be like 500,000. That's kind of 1/3 of their budget maybe, so that's not really an option to do this substantially and work with that. One of our main tasks was to see, okay, how can we do this more cost efficient and simpler? Because obviously we see in other sports that these kinds of systems can be really, really helpful. So for one, we have things like action and pattern recognition. So all the automated annotation that is normally done by one poor person or intern that needs to watch all the videos and then tag all those actions, what they're doing then for technical analysis. Or what is also oftentimes done and what you also see now with the Euro, all this physical data. That is really important for injury prevention, but also optimizing the training to get your players in shape for match demands. Like all those things are by now not really happening in tennis. And we can actually see in this paper that only 7% of people in tennis actually use the typical training mode monitoring that, for example, is widely used in every second division football club. So they are quite lagging behind in this kind of ideas. And it's also obvious why it is more complicated. First of all, you need to bring all the ideas of a really wide team. So that's also what we needed to do within this project. So we needed to build a project and an idea where we combine people from the data scientist, from the medical side, from the sports performance analyst, and then all of which we don't have on this slide, are all the coaches from all the athletes, because they all have individual coaches. So you all need to pool all their information and build a product that they all like. And again, it's really, really difficult to do this for players because every player more or less is a team or a brand. And they mostly also make money off the court with all the nice little commercials that you see with all the tennis players. So that means it's not like in football where you have one team, you give them the sensors, they train, and it's all fine. Because every player is a brand, they might have also different like commercial affiliations with different brands and use different systems. Then they are constantly traveling. It's not that they are at like one pitch training all the time. They are all over the world. So you cannot install, like get there when they are training, install a Hawkeye system, and then install the next 5 days another Hawkeye system with the new tournament. That's just not feasible. And it's also that they are not allowed to wear any wearables during competitions. So the only option is really computer vision. So that's then our goal was to create a relatively cheap and easy computer vision system where we could then feed in video data, preferably from one camera, because that's something that they can easily transfer with the coaches, or from broadcast data to do simple analysis, to speed up the tagging and tracking of for technical analysis, but also get out all the physical load data that we normally would use to training monitoring. And now I give the floor to Max because he will guide you through the process how we set it up.
Exactly. So, yeah, you can imagine that it takes a few steps to go from raw video footage to actual insights. And well, there are some bunches of projects that I would like to outline and give a little bit more insight into the problems that we encountered, but also our solutions and some other funny traits when working with tennis video footage. So that's chord recognition, player recognition, filtering of data, detecting rallies, also important, and also a little bit about how you can find out which player is who at both sides of the net. So starting off with tennis video footage, you can imagine that it's there's a whole bunch of different traits that these videos can have. So we play on different surfaces, grass, well, not all of our players, unfortunately, but grass sometimes. Clay court, hard court, all different colors. There are different camera positions, so sometimes there's a very nice bird eye view, but sometimes we just have to put a camera on a fence and then the angle is less optimal. We're dealing with different quality of footage, different frame rates, also different scenery. So there's a whole lot of different situations that we need to account for when we're making such a system. And there are a few different sort of categories that we like to distinguish. So this is probably grade A footage. So there's a high quality footage. We have a nice bird's eye view position. Very important, the camera doesn't move. I hate these cameramen that do these dynamic positions all the time. And this works very, very well. Then we have this grade B kind of footage where we have a more creative cameraman. And you can also see that our player talent, Griekspoor, is sometimes disappearing because of the crowd and the stands, which makes it, of course, also difficult to track when we can't see him. And then we have third grade, and that's basically more amateur-like footage. So this is at our training center in Amstelveen. The angle is sort of okay, but the quality of the footage is a bit lower. And we see this also, especially with youth players that are traveling a lot to all different kinds of places with a little camera or their iPhone camera. You can imagine the quality sometimes drops a little bit. So this is then the grade C quality footage. Starting off with chord recognition. So ideally you would do this automated, of course, and we have some algorithms in place to do that. And in some cases we just use manual annotation. So for we can automate it when the footage is of high quality, and we also do it when the camera footage is dynamic, or actually the position or the angle of the camera is dynamic. When there's lower quality footage, or when the camera is static, then we can just use manual annotation of the chord dimensions. And we have set up two different models to do the automated recognition detection of chords. A U-transform model and a UNet model. And actually for both models, we can see that it works quite well on high quality footage, but it really drops on lower quality footage, especially that is for the youth transform model. So that really drops in quality whenever for example, the frame rate goes down or the position of the camera is suboptimal. So actually per video, we have to see which algorithm we use and if we use it or we do it manually, because otherwise things like this can happen. So for the row above, that's or the upper row, are results from our youth transform model, and it actually does like a very good job on high quality footage. So for example, that one. So it sometimes really has a perfect prediction of the 4 corners of the tennis field, which we are interested in. And then the UNet model generally scores better on lower to higher quality footage, but very seldom has a perfect recognition of the court. So these are like the performance of these models we have to take into account when choosing a algorithm for detecting the court. We're also looking into more of a dynamic version of both of them. So otherwise, we do manual annotation, and that's basically just clicking on the 4 corners of the field, hoping that the cameraman isn't too creative, and hope for the best. And normally this works, of course, very well when there's a camera on the fence, or when you know there's a broadcast footage where the cameraman just takes coffee every now and then there's no movement. Once we have the coordinates, we do a projective transformation using a homography matrix. This allows us for expressing 2D coordinates from one coordinate system, namely the coordinates of your pixels on screen, to the actual 2D court coordinates. And this works quite well, except for one assumption that you have to make, namely that the players are on the ground at all times, which they are not, of course, they jump. So you make a little bit of an error there, but this is probably the best solution for expressing those coordinates of players from your screen to actual on-court coordinates. Then the next step is the player detection, player recognition. So we use a YOLO V8 model from Ultralytics. It's pre-trained, so we used a pre-trained model, and we actually saw very good results there. So we didn't feel really the need to do a custom-made training for our situation. However, it also offers different sizes of your model, and generally we can use the small for broadcast footage. And when the quality of the data goes down, or of the video goes down, we sometimes look at medium or large size models. And this is the kind of output that you then can expect. So it detects players, but also, or it detects persons, but also different kind of objects. So for example, the ball, tennis racket, I think so as well, some other things. And it gives a little bit of information about each detected object, namely the confidence. So how sure are we that the label that it says is actually that label, so that the person is actually a person. And very important, the dimensions of the bounding box around the persons. So we know how the width and the height of the box around the player. Then, as you can see, there are a whole lot of distractions that we have to deal with. So in broadcast footage, we often have ball kids, we have umpires, coaches, spectators, a whole lot of people. And then there are these alternative and dynamic camera angles. And there are replays, also quite annoying. So we had to do some tricks to get a hold of that. And starting off with the person, so you have to basically find out which of all the detected persons are players. And there are, of course, a few traits that only the tennis players have that the other ones don't, namely velocity in most cases. They also have some dimensions of the box that we expect, but we actually found the best results by just looking at the position of the players. They are different than the other persons. So we use a little sort of heat map index to find out which players are closest to a certain point on field, namely about 1 meter inside of the baseline. And that way we can distinguish which persons are players and which persons are not. And in case it goes wrong, we use some filtering. We have sort of made a custom filter which really fits well for our sort of data. So there are some really specific things we have to deal with. For example, the ball kits and some other traits. And as you can see, once it gets distracted by one of those ball kits, it probably finds a way back to the right player in the end. Yeah, so the next challenge would be, especially with broadcast footage, to find which moments in time are actually rallies and which moments in times are not. And we also tried a whole bunch of different things here. And we found best results by looking at the sizes of the bounding boxes of both players. And well, as you can see from the pictures on the right, for example here of John McEnroe, if there's a bounding box around John McEnroe, it has a very different size than you would normally expect during a rally. So we use that kind of information to filter out those moments. So for example, here you see a timeline. The blue line is the height of the box of the player on the far side of the net, smaller, of course, than the one that's more close. And that way we can distinguish between what's probably a rally and what is probably not. And then next we are interested in when the rally actually begins. And we use a rule-based approach with the information that we already have. So you could also train a model that recognizes serve, for example. But we do it this way. So there needs to be a sound peak. Both players must have expected serve and return positions. Both players must have close to zero velocity. And then we have some logic in place to distinguish first serves from second serves. We already know that second serves always need to be after first serve. So there's some information there that you can use to distinguish both of them. Yeah, and then the last step is understanding which player is which player. And we use color clustering for that. So what we do is we set for a random or for 5 random frames during the match, we assign which player is on which side of the net. Then we do detection of the player. And then we do k-means clustering with 5 clusters to make sort of a color palette of that player. So for example, here this works very well. So we have a color scheme for Taylor Fritz and also one for Tsitsipas. And well, you can already see there's a distinctive color, which really helps us. This strategy works very well for all but one tournament, Wimbledon, where you have to wear white. So that gives a little bit more manual annotation work, as you can imagine. And as a result, we can actually run this and collect some data.
Yeah, with all these processing steps, what we get at the end is 10 hertz player coordinates, X and Y positions that we can actually use. We get the rally time, so we can actually cut out all the videos and give them to the performance analysis to then do the annotation. So we can actually more or less cut down 2 hours of video data into maybe 20 minutes that they just look at, which saves a lot of time. Time is money. And also have the serve and return annotation already, so they also need to do less of the annotation again, which saves time. But for us, what is really then also important and what we get to the next steps is all those X and Y coordinations, because that we can use then now for what we introduced before, are these ideas of load measures. And obviously the next step was how can we trim down all those possible load measures that are out there. So these are just like wide range cloud plot of what you could do, like sprint distance, time spent in tout zones, power output, number of sprints, jumps, whatsoever. Like all these kinds of things would be possible to detect. But what are our staff at the federation is actually interested in? So the next step was now to convince them to actually use the system, because the buy-in is the most important, especially in a sports federation. We got the idea, okay, we really focus it on them. So what we did is we did semi-structured interviews with all of the divisions to figure out, okay, what kind of ideas did we actually want? Explain them the different matrices, pros and cons and benefits. And based on those interviews that we did, we had them all typed up and written down and did some theme-based analysis to automatically detect, okay, what are the things that they're actually really interested in and building upon. And based on that, we are now busy to actually set up a dashboard in Tableau, which has also mostly been with ideas on distance traveled from one stroke to the next stroke, number of sprints, and a kind of a mean sprint distance that they have. So really rather basic, simplistic measures, but those are measures that they are really interested in. And then the next and last step to actually look at their buy-in is that we will also do, again, another round of interviews to see if they actually like the dashboard and how do we use it to apply it. Because like they already took quite some time, to more than 2 years, to be happy with the idea that we do this project. And now they really get, oh, those physical data is really interesting. And they really bother Max more and more. Can you run also this game? Can you also run this game? So they're really catching up. And we think if we have this dashboarding in place, then it will really catch up and they will really be interested. And we can increase the number of 7%, at least within the Dutch Federation, hopefully of 100% pretty soon. So that's everything for us. And now we're looking for your questions.
Thank you for the talk, really interesting. In football, data is a big part nowadays. And you can also buy data, I believe. You mentioned earlier that the associations don't have that much money, but is it also possible in tennis to buy data?
Just have to get the microphone back to yeah, definitely. So we also buy data from Hawkeye, for example. And the only restriction there is that the players, of course, had to have a match on a Hawkeye court. So for matches where we have Hawkeye data or are able to or have budget for to buy Hawkeye data, then we will do that. And in other cases, we have to be creative ourselves. Yeah.
Sometimes a machine learning model does this thing called artificial stupidity, where it makes a wrong prediction, but it's kind of hilarious in hindsight. In all of your experience doing this work for the Tennis Football Association, what is the funniest thing you've seen go wrong with a machine learning model?
Yeah, so that must have been the interaction between me and a ball kit that actually I wasn't really sure about the detection of rallies just yet. And there was a ball kit who ran from this side to the other side, but forgot the ball and then had to run back. And I thought it was a rally going on because it's a very familiar movement. Took a while to figure out. Yeah.
I think we had another example. So we also did an evaluation study just on the physiological parameters like sprint distance, velocities and everything, and if they would work properly. And they worked probably like in the lower side and in the middle of the court, but we actually had a little bit of issues when they would come really close to the net because the pal, like the stance of the net, was then sometimes detected as the player and more confident as the player than the player itself. And that's actually, we just figured that out doing those special testings because we didn't have that many instances of player being that close to the net stance in a real match. So on the normal match data, we didn't figure it out. But then on the specific testing, we run into that, yeah.
Hey, Andre, RCA Partners, Amsterdam. A question of mine is, in sports analytics, it's often difficult to couple your analysis and your data to tangible impact on the pitch, or in this case, on the court. And how much have you found that challenge to be, first of all, central maybe to what you're doing? And second of all, what kind of approach do you have to linking the analysis to actual tangible impact on the court, on a game?
So maybe I thought first of all, it's more the day-to-day business of Max. But one thing we definitely did see is that oftentimes coaches don't really have an idea what are really the match demands. So how much distance do they actually, how many sprints do they have, and how does it change over the time course of the game? So they had really no idea about that. And after showing that, and also like quite a steep drop with some of the players, and that they are nowhere close of some of these demands in their training sessions, they really got interested. And that's where we sparked the interest. But it definitely took some time to convince them, as they also think like tennis is more of a skill sport. So technical, like physical capabilities are not that much of an issue sometimes.
Yeah, and it also helps that a large part of this is especially interesting for the strength and conditioning coach, who often already has more of a scientific background. So he can also help as sort of a translator to the head coach. And convincing the head coach is always more tricky. So sometimes when there's the easiest case sometimes is when the coach has an assumption and he wants it to be confirmed. And then we get into the data and we hope that we can confirm it for him. Isn't always the case, but those things help as well. Yeah.
Does the coach ever come back and say your insights have helped concretely in a game to turn a game around or change something?
Yeah, so the question was, did the coach ever come back and say, okay, this insight really helped us? Yeah, so around Davis Cup matches, we do also analysis for the opponent, or not for the opponent, about the opponent. And one thing that we saw in the data was, for example, that we had to serve more towards the body of the players instead of wide and towards the T, what we call, towards the middle. And we actually got some positive feedback back there. So sometimes we get nice results back. Yeah, some impact. Yeah, cool.
I'll go here first. Hello. Do you plan to move move forward with something like I don't know, stroke analysis or something in a kind of semi-automated way, or what are your next plans for this kind of data?
I would love to. It's also a bit of an issue of having enough time to develop. At first, we really had the goal to do the physical part. So we say we make some sort of a distinction between all the tactical analysis and the physical analysis. And once we wrap this up, we might move forward. But not sure yet. Also because there are, like we said, other suppliers who also can deliver that kind of information. So it's just a question whether it's as beneficial to also develop that. Yeah, but it's very doable. Yeah.
Maybe also in this note, if you work with federations, you need to introduce things slowly. So step by step, they really need to get used to working with one dashboard, seeing the value in that, and then you can slowly expand. So every new step takes quite some time for them to catch up, understand it, and see the use of it. So sometimes you want to do things, but it's really nicer to start with something simple, really help them explain that one, and then go further. So that helps them with the buy-in. Otherwise, they don't like it anyway, and you're out of a job. We don't want that.
I think we have time for one last question. Was in the back? Same question. Well, one more opportunity then.
If I understood correctly, you said you did color segmentation to identify the players. How would you do that on a tournament like Wimbledon, where the players usually dress just all white?
We pray. It's undoable with this technique. So we do more manual annotation with in those cases. Yeah. And you don't have to do it, of course, every point, because we with tennis we work with the system where we can expect when someone goes from the one side to the other one, because every 2 games we change sides. So that information we can use to make it sort of doable. But it doesn't work for those kind of situations when players have the same color scheme. Yeah.
Then I'd like to thank Max and Matthias for the presentation.